Millions of people regularly consume magnesium to treat anxiety and insomnia. The physiological rationale is sound. Magnesium acts as a central nervous system depressant and an NMDA receptor antagonist. The NMDA receptor is a specific ion channel in nerve cells that typically allows excitatory signals to pass. Yet a clinical paradox persists. Patients frequently ingest massive doses of elemental magnesium, often exceeding 700 milligrams, and experience absolutely zero neurological benefit. Instead of improved sleep architecture, these massive doses of inorganic magnesium rapidly induce gastrointestinal distress. Throwing sheer elemental mass at insomnia fails because the biological bottleneck is the formulation, not the quantity. To understand the failure, we have to examine two distinct molecular structures: inorganic salts and organic chelates. The most common inorganic salt is magnesium oxide, which exists as a simple, tightly bound ionic lattice. Contrast that with an organic chelate like magnesium bisglycinate. Here, the central magnesium atom is physically protected within two rings of amino acids. Both of these molecules must first navigate the highly restrictive epithelial barrier of the human gut. The epithelial barrier is the single layer of tightly packed cells lining the intestine that strictly controls what enters the bloodstream. Magnesium oxide boasts an extremely high density of elemental magnesium, but it suffers from a notoriously poor intestinal absorption profile. Clinical reviews consistently highlight loose stools and gastrointestinal distress as the most common adverse effects of these standard inorganic formulations. A supplement's clinical efficacy is entirely dictated by its molecular vehicle. Inside the lumen of the small intestine, we find the microvilli epithelial barrier. The lumen is the hollow inner cavity of the digestive tract, and microvilli are microscopic cellular projections that significantly increase the surface area for absorption. When the magnesium oxide lattice enters this highly acidic environment, it rapidly dissociates into individual magnesium and oxygen ions. The liberated magnesium ions attempt to pass through tightly regulated epithelial ion channels along the intestinal wall. These specific ion channels saturate rapidly, leaving the vast majority of the magnesium ions stranded in the gut lumen. These stranded ions create a powerful osmotic gradient. An osmotic gradient is a physical imbalance where a high concentration of solutes on one side of a membrane pulls liquid toward it. This gradient forcefully pulls water molecules out of the surrounding intestinal tissue and dumps them directly into the lumen. Rapid fluid accumulation and swelling of the intestinal space is the mechanism of an osmotic laxative. The intended neurological treatment is physically flushed from the patient's system. Inorganic magnesium treats the gut, not the brain, rendering it useless as a targeted therapy for insomnia. Returning to the intestinal epithelial barrier, we can track the journey of the magnesium bisglycinate molecule. Unlike the oxide form, the chelated structure of bisglycinate remains firmly intact in the harsh acidic environment of the gut. It approaches an alternative cellular pathway, specific membrane proteins known as peptide transporters, which are designed to absorb proteins, not minerals. According to the dipeptide absorption hypothesis, the gut recognizes the glycine amino acids and allows the entire complex through as a single unit. A dipeptide is a molecule consisting of two amino acids bound together. This mechanism completely bypasses the easily saturated ionic magnesium channels that trapped the oxide formulation. Intact transport grants that magnesium bisglycinate exceptionally high overall systemic bioavailability. This alternative pathway even allows absorption in patients who have naturally impaired ionic mineral transport. The intact dipeptide complex smoothly passes through the lipid bilayer, exits the intestinal tissue, and enters the bloodstream. Organic chelates effectively hack the body's digestive security checkpoints, successfully delivering the active payload into systemic circulation. From the bloodstream, the payload reaches the blood-brain barrier, the critical hurdle for penetrating the central nervous system. The blood-brain barrier is a highly selective membrane that protects the brain from circulating pathogens and solutes. Due to tissue-specific uptake, magnesium bisglycinate preferentially elevates brain magnesium levels over muscle tissue. Inside a synaptic cleft in the brain, the dipeptide complex finally splits apart. The synaptic cleft is the microscopic gap between neurons where chemical communication occurs. The liberated magnesium ion physically plugs the pore of an NMDA receptor, blocking excitatory calcium from firing. Simultaneously, the magnesium ion potentiates GABA-A receptors, increasing overall inhibitory neurotransmission. GABA-A receptors are the primary inhibitory channels in the brain that slow down nerve signals. The leftover payload, the chelated glycine ligand, acts independently as its own inhibitory neurotransmitter. This dual-action neuromodulation, blocking excitation while promoting inhibition, provides the precise biochemical recipe for lowering core body temperature and inducing slow-wave sleep. We can verify this biochemical theory using empirical data from a recent double-blind randomized controlled trial on insomnia. A randomized controlled trial is a clinical study that randomly assigns participants to either a treatment or a placebo group to test efficacy. This line graph shows mean insomnia severity index scores over a 28-day intervention for placebo versus magnesium bisglycinate. At baseline on day 0, both groups began with nearly identical elevated insomnia severity. The Insomnia Severity Index is a standardized clinical questionnaire used to measure the nature and severity of sleep disturbances. Observing the trend, sleep quality rapidly diverges, with a steep, significant drop in the bisglycinate group scores by day 14. This sleep improvement maintained a statistical significance, with a p-value of 0.049 through the end of the 28-day trial. Reviewing the safety profile confirms the hypothesis regarding osmotic side effects. This bar chart compares total adverse events from the trial. There were 7 in the placebo group versus only 2 in the bisglycinate group, with 0 gastrointestinal-related dropouts. This statistically significant neurological success was achieved with only 250 milligrams of elemental magnesium. Compare that small dose against the 700 milligram inorganic doses that routinely fail and cause loose stool. Organic chelates offer a decisive systemic advantage. In clinical pharmacology, the molecular vehicle is just as critical as the mineral payload.